Hey there! There's no doubt that donating blood has saved millions of lives worldwide. But what many people don't realize is that its benefits aren't just limited to the person receiving the blood. Studies have shown that regular blood donation can significantly benefit the donor as well. Blood donors often have a reduced risk of heart attacks and strokes, thanks to the lowered iron levels in their bloodstream. It's truly a life-saving act that offers benefits on both ends. But beyond the life-saving importance of this process, there's a fascinating question that often comes to mind. What happens to the donor's DNA during a blood transfusion? Does it mix with the recipient's DNA? And if it doesn't, is it ever possible for someone to have two sets of DNA coexisting in their body? That's exactly what we're diving into today. Welcome to the channel. If you're new here, make sure to hit that subscribe button and turn on notifications so you never miss out on our latest videos. We tackle intriguing questions that might keep you awake at night, wondering about the mysteries of science and life. Let's dive right in. To answer this question, let's first take a closer look at what blood is actually made of. Blood consists of several components: red blood cells, which make up about 45% of the blood. These cells are responsible for carrying oxygen throughout the body. Plasma, which accounts for approximately 55% of the blood. Plasma is the liquid portion that carries nutrients, hormones, and waste products. The remaining 1% consists of white blood cells and platelets, which are involved in immune responses and blood clotting respectively. Out of these components, the only one that contains DNA is white blood cells, also known as leukocytes. Since white blood cells make up such a small fraction of the blood, the actual amount of DNA that could be transferred during a blood transfusion is incredibly tiny. But here's where it gets interesting. Even though some DNA is present in the transfused blood, it doesn't usually cause any lasting effects on the recipient. Here are 3 key reasons why. Blood processing. Before blood is transfused, it undergoes rigorous processing. Many blood banks use centrifugation to separate the blood into its main components: red blood cells, plasma, platelets, and white blood cells. In most cases, white blood cells are removed entirely before storage to reduce the risk of immune reactions in the recipient. This step significantly reduces the amount of foreign DNA present in the transfused blood, the immune system's defense mechanism. Even if some white blood cells remain, the recipient's body identifies the foreign DNA as an invader. The immune system works tirelessly to break down and eliminate it, treating it like any other foreign material. Short lifespan of white blood cells. White blood cells only live for about 3 to 4 days. Since they don't replicate or multiply, any foreign DNA they carry doesn't have the chance to spread or integrate into the recipient's body. This natural limitation ensures that the donor's DNA doesn't have any long-term impact on the recipient. So, does that mean the donor's DNA completely disappears? Not exactly. Studies have shown that small amounts of foreign DNA can remain detectable in the recipient's bloodstream for a short period. In most cases, this period ranges from 7 to 8 days. However, in rare cases where a person receives large volumes of blood over an extended period, such as during major surgeries or medical emergencies, the foreign DNA may persist for up to 18 months or even longer. While this is fascinating, it doesn't usually lead to any significant changes or effects on the recipient. Rare complications and effects. Although rare, there are some documented cases of temporary effects caused by transfused DNA. For instance, some recipients have developed new allergies after receiving a blood transfusion. Imagine someone who's eaten strawberries their whole life without any issues suddenly developing an allergy to them after a transfusion. This has been observed with other foods, medications, and even environmental factors. In rare instances, recipients have reported unexplained fevers or immune responses, where the body reacts to the foreign DNA as though it were a harmful invader. What about having 2 sets of DNA? While it's incredibly unlikely for a blood transfusion to result in a person having 2 distinct sets of DNA, there are rare and fascinating cases where this does happen. These cases are referred to as human chimerism. Here are 2 notable examples. Bone marrow transplants. Bone marrow is responsible for producing blood cells, including white blood cells. When someone undergoes a bone marrow transplant, often due to conditions like leukemia, they receive donor marrow to replace their own damaged or diseased marrow. Once transplanted, the donor marrow begins producing blood cells that carry the donor's DNA. Over time, the recipient's blood may exclusively contain the donor's DNA, while the rest of their body retains their original DNA. Twin chimerism. During pregnancy, if one twin dies early in the womb, the surviving twin may absorb some of the other twin cells. This results in the surviving twin having two sets of DNA in their body for the rest of their life. A famous case involved Karen Keegan, who discovered through genetic testing that she wasn't the biological mother of her children. Further investigation revealed that her DNA came from her absorbed twin. Microchimerism in pregnancy. During a normal pregnancy, small amounts of a baby's DNA can migrate into the mother's body. These fetal cells can remain in the mother's body for decades, a phenomenon known as microchimerism. Some researchers believe these cells may even play a role in healing and regeneration in the mother's body. Expanding on microchimerism. Microchimerism doesn't only occur during pregnancy. Research has revealed that these fetal cells might have fascinating roles, such as aiding in tissue repair or influencing the immune system. However, their presence isn't always benign. In some cases, microchimerism has been linked to autoimmune conditions, where the body's immune system mistakenly attacks its own tissues, potentially triggered by the foreign cells. Beyond blood transfusions, there's another form of human chimerism that occurs naturally. This is called tetragametic chimerism. It happens when two fertilized eggs merge into one embryo in the early stages of development. The resulting individual carries two sets of DNA in their body, derived from two separate zygotes. This phenomenon is rare but can lead to fascinating outcomes, such as varying skin pigmentation or discrepancies in genetic tests. What about forensic science? The presence of two sets of DNA in one person can complicate forensic investigations. Imagine a scenario where a DNA sample from a crime scene doesn't match the DNA in a suspect's saliva, but does match their blood. Cases like this have occurred, leading to breakthroughs in understanding human chimerism and refining forensic techniques. Blood transfusions in modern medicine. Thanks to advancements in medical technology, the risks associated with blood transfusions have significantly decreased. Stringent safety protocols ensure that donors and recipients are matched for blood type and screened for diseases. Innovations like artificial blood substitutes are also being developed, potentially eliminating the need for donor blood in the future. Final thoughts. The human body is a remarkable and complex system. Whether it's the process of donating blood, the intricacies of DNA, or the rare phenomenon of chimerism, there's always more to learn. While it's rare for a person to have two sets of DNA, these exceptions highlight the incredible diversity and adaptability of life. If you've ever been curious about the mysteries of science or have questions that keep you up at night, leave them in the comments below, and we'll answer them in future videos. If you enjoyed this video, don't forget to give it a like, share it with your friends, and subscribe to the channel for more fascinating content. See you in the next episode. Bye.